We will agree. We will record the meeting and then we will put it on our website.
And the other part of the meeting will be dedicated for your questions. So if you have a question of mine, you can put in chat, and after that I will make the question what will be on the chat to François. We think the meeting will be finished around 6:30, 7 p.m. UTC at maximum, because we have the speech of our president and we have to know what's going on in France in the next weeks and what's not going on, because we would be quarantined we think for at minimum 3 weeks.
At least you know what's going on.
Okay, so please make a short presentation of yourself and anyone who is ready, maybe Thomas.
Okay, I'm Dr. Thomas Herring. I work at Western Nevada College in Carson City, Nevada. I'm a physics professor and I'm the director of the Jack C. Davis Observatory that's right here on our campus.
Thank you. Daryl?
Sure. I'm Daryl Johnson from the University of Saskatchewan in Canada. I'm an astronomy instructor and run the observatories here too.
Anatoly?
I'm Anatoly Miroshnichenko. I'm a professor at the University of North Carolina, Greensboro. Together with Steve Danford, who is trying to connect now, we run the Free College Observatory in North Carolina, which has an 81 centimeter telescope and a shell spectrograph from Chauliac.
Alan?
Hi, I'm Alan Chu. I'm actually a grad student at San Francisco State University in San Francisco, California. And actually we have 2 Chauliac spectrographs right now, which are, I'm in charge of trying to get them installed and make use of there. So we have an Echelle and we have an L high-res 3. And they're both, right, because of COVID-19 there, we can't use them yet. I'm trying to set it up to be able to use remotely there on a 30-inch telescope, that we have out in the county there. So that's where I am right now.
Rick?
Hi, I'm Rick Francisco from Evergreen Valley College. I'm an instructional lab technician. I work with Celso Botaja here at Evergreen Valley College, and he wants me to get as much information I can about the spectrograph that we hopefully will try to purchase.
Okay. Ron?
Oh,
Ron, are you there?
You're on mute. You're on mute.
Trying to save some bandwidth. Sorry about that. I'm Ron DiUlio. They call me Starman. I'm the director of the astronomy program at the University of North Texas, and we have a telescope farm. We have approximately 16 telescopes of small aperture, and we are currently operating most of them remotely. And this has been a huge challenge as we try to adapt spectroscopy and instrumentation for that. And so I'm really interested in making connections with some of you folks, especially those of you that are in university like Alan, and so that's what we're here for. We're looking at the possibilities of how we can introduce spectra into our remote telescopes.
Bruce?
Hi, I'm Bruce Pollard. I'm in Houston, Texas, actually in Kingwood. We have an observatory that supports the local school system and the local junior colleges. And I'm kind of the spectroscopic manager part of that. There are several of us that support that. So Ron, we're actually nearby, and I've got a son that goes to UT Dallas. So we could connect, and I could help you out. I have a PhD in chemistry, and I did spectroscopy for a long time for a big company, but now I'm retired.
Well, good. We can talk University of Texas in Dallas of working. I've been doing some remote telescope labs for them since they can't use any labs face to face. And so they've been using our facilities, and I've been hosting them. So this would be great. We'll just get everyone, have a big Texas party.
Yeah, there you go.
Siri, thank you. Siri?
I'm a graduate student at the University of Toronto working with Bob Abraham. And I'm also working with one of the Sheliak spectrometers, the L high-res, and working on setting that up remotely for my project. It's part of my project.
Thank you. Do I forget anyone? Arne, maybe?
Yes, I'm Arne Hinden. I'm a research astronomer and past director of the AAVSO. Still very active in handling their AVSO-net robotic telescope network. And because both of the telescope in my backyard as well as that network, I'm interested in the Uvex.
Okay.
Okay.
I see Steve is here, but he's mute.
Yes, Steve?
Steve, can you connect? Because looks like he had some problems. He was in and out. Yeah. Steve, can you hear?
While we're trying to get to Steve, Arnie, thank you very much for the CMOS recommendations for our scopes. We have gone CMOS almost totally with our scopes, and the ASI Q 6200s and the other very good cameras. Amazed at how.
Good to hear that.
Yeah.
Okay. So maybe we can begin the presentation.
Yeah.
François.
Okay, so we start with the presentation. Well, this is a real pleasure to talk about this product. This is really the first official announcement that we do, and this is a real pleasure to do it with you. Of course, well, we are not too numerous online, so don't hesitate to interrupt me if you want at any time, and ask questions if something is not clear. And please only ask easy questions, because I don't want to be in bad shape. No, I'm kidding. Can I connect? Well, I will. Alain, I need the connection to the sharing authorization of the screen. Can you do that for me?
I'm trying, but.
Just sur mon nom, tu as mort en fait la plus d'outils. Tu vas sur mon nom, la flèche vers le droite, et tu m'autorises à.
Yeah.
Wow, what a suspense.
Yeah.
Okay, so.
No, I'm going to put you in that.
C'est bon?
Non.
Tu vas dans la liste des noms? Tu vas dans la liste des noms?
Oui, je sais. Oui.
Et tu as un mort? Et là, normalement, tu as hello sharing ou un truc comme ça.
No. I put you in. Now you can share your screen.
Okay, so now I am the host. Okay.
Yeah.
Okay, so I do. Tell me when you can see my screen.
Yes. Yeah.
It is? Okay, yes. Perfect. Okay, so let's go ahead. Sorry for the bad starter. Well, here is the Uvex. This is the new instrument that we are talking about for officially for the first time. Well, very probably you have already heard about it because we have already write papers on our website. We had already one meeting. It was in French, one workshop, maybe 2 months ago, 3 months ago. I don't remember exactly, with the French team who was involved in the project at the beginning, but now we are really in the official announcement, and so this is the instrument, and well, I have the sample with me, I have the prototype with me. Maybe you can see it, and I will show with more detail in few seconds. So what is the Uvex? So when we try to define this instrument, which is a challenge, I think that this is the best definition. This is a new generation multi-purpose achromatic spectroscope for small telescopes. Okay, and then we will go in detail to each of these points to define exactly what it means. So the idea is always for us to make as good instrument as possible from optical quality standpoint, and we really want to have the best possible results during your observations. And really, I think that these instruments in the Shellac product range will open a new window, a new universe to the small telescopes, especially because we can go very far in the UV and in the infrared, in the IR. Okay. Well, a quick message is very quickly, just to start. The optical design has been made by Christian Bril. I guess that most of you know him. So he's a French pioneer in astronomy and spectroscopy, and he's very involved in most of the products of Shellac instruments, and we are working very closely together, and it's always a great pleasure. And so he was at the origin of this project, and in fact the Uvex project is a wide project that was launched at the beginning out of Shellac, and what we propose today is a Shellac version of the Uvex. Okay, the idea of the Uvex is to have a basic optical schematic and to propose some 3D printed parts to make your own instruments if you want. And so we already have the same optics, and we just made it industrial and with a good mechanics, and not only with a 3D printing, to have something very strong and easy to use at the telescope. So this is really the first announcement. So it may happen that we still have some minor changes, because we are really starting the production phase, and it may happen that we have some slight changes. And I told you that we already wrote a paper, even 2 papers, I think, on our website to talk about the first slide. Okay. So to talk quickly about what can make this instrument. These are a few examples of spectra that has been taken very recently. The top image, I hope that you can see my mouse, the cursor of my mouse. The top image here is a single shot with a black and white camera with the 300 groove per millimeter grating. This is really a single shot, and you can see the bottom part here gives some reference lines, and just so this is a sun spectrum, of course. I guess that you have recognized it. This is a sun spectrum, and you can see here the H and K lines. So we are in the deep blue, below 4,000 angstroms, and you have H alpha here, okay, all the graphs are aligned. So H alpha is here, and it shows that with the most of our instruments so far, we covered from the blue to the to the red, but just after the H alpha. Okay, so if you take, for instance, an ALPI spectroscope or a LISA spectroscope, you should cover something like the bottom figure, and then we reopen all the blue parts here, and we can go even deeper in the blue here, and we can also cover a wide range of the infrared. Okay, and again, this is a one shot. This is not a mosaic of different. This is not a merge of different images. This is really a single shot with a 300 groove per millimeter grating, and with a quite wide sensor. I think it was taken with an ASI 294, which has more than 19 millimeter long. Okay, so this is to give you some idea of what you can do. So this is the same image with a color sensor in the bottom. Of course, this is very similar. And this image, the third one, is also the same, but in this case, we have put a filter order because you know that in this range, we have a mix of the first order of these wavelengths, the infrared wavelengths, and it is mixed with the second order of the blue. And then when we put a filter order, of course, we cut all the blue parts, but we don't have anymore any mix in the red and infrared part, and then we have a much better contrast. Okay. So this is what we can do, for instance, with the Uvex. Okay, so these are some real observations made in this case by Olivier Garde regarding two different stars, especially looking at the H and K lines. Okay, and we also have some, maybe you have already seen that because this image has been published by Christian Bril. So he made these images with the 3D printed prototype, not with the Shellac Uvex prototype, but the optics is exactly the same. And we can see, for instance, with the Vega, well, maybe you are familiar with this infrared part of the spectrum, but I know for me and for most of the amateur astronomers or people who are not familiar with this kind of instruments, this is really the first time that we can go so deep in the blue. Okay, and we can see so many details in the blue part of the spectrum. Okay, I'm sure that all the scientists that are online can perfectly understand what it means. Okay, so when I say this is a new generation instruments, what does it mean? It means that really, in fact, this is the first time for a very long time, several years, that we are able to present a new instrument, and really we have designed it in a new way. Well, the first thing for me, you know, I'm a mechanical engineer, and this is important. Mechanics is important for me. We have really an advanced mechanical design. So in the past, we tried to have a very cheap solution and efficient solution and the tricky solution, I don't know the exact word, to save the cost of the instrument. But the result is that sometimes the tuning are not very sensitive, and sometimes the instruments are not very easy to tune. So this time we have really put the mechanics at a higher level, and then we have made such a way that we can have very good tunings of the instrument. Okay, so in this new generation also, so I like to say that this is the first instrument of the new generation. Something very important also, which is in fact new to our products, we don't need anymore to open the box to tune it. Okay, so all the tunings that are required for the instrument, we can access it from the outside of the instrument. Okay, and so no tool is required to manage it. And well, I will show you later on the prototype. Well, and the other thing, in the easy to use part, there is of course the weight, which is very low, and it is very compact. Again, you can see it. It is well, compared to my hands or my head, you can see that this is very a small instrument. It is smaller than the LISA or the LARES-3 for who are familiar with these instruments. Okay. Also, something very, very important. We know that more and more people want to use these spectroscopes remotely. We have all the software way to do it, and now we are really ready with the Uvex to remotely operate the instrument. Especially, well, we'll add a complementary module on top of the Uvex that will control the grating angle here. Okay, so I can, maybe you can see it. I can change the grating manually in this case in the basic way, and I can focus with this button here. I can focus the spectrum again from the outside, and these two operations will be made remotely with an optional module. Okay. And also something important is that we have cameras are changing. So you know that we are switching from CCD to the CMOS. Ron, you did talk about the IMX 455 or the camera, the ASI 6200, if I'm right. And so this is exactly the kind of new generation of camera that is in front of us. And again, they are allowed to go very deep in blue compared to what we used to have so far. And also the telescope are changing. The telescope landscape is changing, and we have some. Oh, I see that Wayne is trying to connect. So maybe I didn't check before. And the telescope, now we have more and more telescopes, small telescopes with the purely mirror architecture. And this is something good to do spectroscopy, of course, because there are no chromatism. I'm especially thinking about the Newton telescopes, not for the Uvex, but for other kind of instrument, and especially the Ritchey-Chrétien telescopes that are purely mirror. Okay. Sorry. Yep. I'm going too fast. So just a few pictures. This is the well, maybe Wayne, you did join us. Hello, Wayne. And you can, I hope that you can hear me. So these are a picture of this is a Ritchey-Chrétien 12 inches. It was at the OHP last summer, and you can see the Uvex here with the LP guiding module and the LP calibration module attached to the box. And this is the inside of the Uvex, okay, of the mechanic that we have. When I told you that we had the high quality mechanical design, you can see this part here, which is a very complex part. Well, compared to what we made before. This is a single part that attach the telescope on one side and the camera on the other side. So it means that one strong part attached together the camera and the telescope. So there is no risk of flexions and things like that. Okay, so the dimensions, this is small. This is a small instrument. These are millimeters here. And the instrument itself, without any complementary module, it is roughly 1 kilogram. So it's quite light, of course, and there is no problem to put it behind the telescope of 2 days. What else? Well, I already talked about the way to remote it. So we can control the focusing by moving. If we look at the 3D view here, you can see that so this is what we call the M1 mirror, and so the light comes from the slit here, goes to this mirror, is sent to the grating, which is in the middle, and sent to the secondary mirror, so the M2 mirror, and then the light is sent towards cylindrical lens here and to the CCD or CMOS sensor here. And we do the focusing by moving very precisely the M2 mirror, which is mounted on a holder that is very strong, robust, with no movement and no mechanical gap. Okay, so we'll be able in few months from now, not with the initial module, but in few months from now, we'll be able to control the telescope focusing and the grating angle. Okay, we will not be able to change the grating remotely. We tried to do that at the beginning, but you know, it's really a question. If I come back, we cannot see very well here, but in fact, there is absolutely no room. All the critical path is around the grating, and there is absolutely no room around the grating to make something changeable. We did try. Okay, so now I said at the beginning that this is a multi-purpose instrument. What does it mean? This is an important point. This instrument can be used in several ways, in very different ways. And that makes this instrument very useful to make many different kind of various observations. First, we can change the grating. Okay, so this is the very an important point. We have a choice between 150 groove per millimeter up to 1,800 groove per millimeters. So we will have 5 possible gratings, and maybe more in the future with the different blaze angles or blaze wavelengths, but for the moment we'll have 5 different gratings. And so this is the first thing. We will reuse the LP guiding and LP calibration modules. So it means that the instrument itself doesn't have any guiding or calibration feature. So it means that you can put the thing any way you want. So you can even use this instrument on the table. You know, you can put that on the table. You have the slit entrance here. You have the camera, and you can play with some any light or do the experiments you want. This is important, I think, for teaching. It can be used also. Well, it is designed and it is optimized for small telescopes. So the reason is very simple. A small telescope means that the star image at the focus plane is small, okay, and then we can have a small slit. If we have a bigger telescope, we'll have a bigger star image at the focal plane, and then if we want to catch all the light of the star, we need to open the slit, and then if we open the slit, we will reduce the resolution. Okay, so if we want to keep the resolution, we have to use it on small telescope. And when I say small telescope, say I think the optimal is probably 300 millimeter or even lower. I know that Christian Bull loves to use very small telescopes. There is a one, it's a 5-inch telescope, a very small one, a Takahashi one, and he loves to use it because it says that it gives very, very good results. Okay, but we can really go up to some medium telescopes, and well, the same Christian Bull who says, well, make sure that everybody understands that this is made for small telescopes. He is also the one who did test this Uvex prototype, the one I have in hand, on a 1-meter telescope in close to Nice, in the south of France. So, and he says, okay, on a 1-meter telescope, it is not optimal. For sure, it is not optimized, but it works. So, and the instrument is so cheap compared to all what you can find on the market that this can be a good solution. And so you can do it. It is for small telescope, but you can use it on another one. It is also used for the f8 or upper telescopes, so some slow telescopes. But again, you can go down to f5. So I mean, if you go to f5 telescope, you will catch all the light. So you will have almost no loss and no vignetting inside the instrument. The problem is that the image quality is not as good as with the f10 or f8. Okay, so well, this is for optical reasons. We can go in detail if you're interested in. This is really due to the optical architecture of the instrument. But the slower you are, the better will be the quality of the image. You can go very far in the blue and in the red, okay, compared to all we had before. So this is probably the most important thing. So if you want to observe in the UV, you can do it. If you want to observe in the visible, you can do it. And if you want to observe in the near infrared, you can do it. We can also adapt fiber at the input. So I hope that you can see it. So you can see here the slit holder, which is exactly the same as the ALPI slit holder. And in fact, it is attached on a small part that I can remove. And if I return these parts, I can put on it a Thorlab fiber connector. Okay, then in this case, I can just use the instrument with the fiber. And by the way, this is something that we will use during the manufacturing process to tune the instrument. In fact, we use a fiber, which is the best way to test and tune the instrument. And well, you have seen in the images that if we observe in the near infrared, there is a risk of order overlapping, and then we have put some room behind the slit here. Again, in this area, we can put a small filter behind the slit to especially to have an order filter, if you want. So all these different options and configurations make that you can really do high variety of observations. So this is how to change the grating. Again, you don't need any tool, so I can do it in real. I just have to turn this button, and which is a cap on the grating module. Okay, I remove it. I hope that you can see what I'm doing right now, and I can remove the grating. Okay, so it's very simple. And when I put it back in place, there is an index, and we push on the grating, so it means it comes back exactly in the same position. Okay, and then you can really remove the grating and put it again and continue your observations without any problem. Well, of course, this is not recommended to remove the grating during the night, but you can do it. Okay. Regarding the resolutions, well, this question is quite complex, in fact, because we have different gratings. We can use different slits. Well, this standard slit is 23 microns wide slit, and the same as ALPI, for if you are familiar with it. And we have tried to define what are the resolutions. So this table is made. This is a theoretical calculation based on the ZMAX optical software, and well, I'm quite confident that this is. I think these are quite conservative values, and in real life, we should have slightly better values, but I want to be sure. And we have given here the different gratings, so 150, 300, 600, 1200, and 1800. Okay, and we have made a measurement at different wavelengths, so from the deep blue to the near infrared. Okay, and well, this gives you, for this 23 microns value, it gives an idea of the different resolutions. Okay,
François?
Yes?
Could you check the waiting room, please?
There is nobody in the waiting room.
Oh.
There should be.
Yeah.
Uh-huh.
I'm here. I was late.
Okay, it's okay.
No,
So
well,
it's an old message. Sorry.
Yeah. Maybe yeah. Okay, it's an old message. Maybe you did wait for a little time because I didn't see you before. Sorry. So this is the summary of all the resolution. Of course, this is these value are the resolution power, and you know that the resolution power is very dependent of the wavelength. So be careful with which value we're talking about. We usually well, in normal condition, most of time the spectroscopes are given at 550 nanometers. So this is why we have put this value. But most of our Shellac instruments are given around H alpha, which is close to 650 nanometers. So this is why we have put these two different values depending on how you want to compare to other instruments. Okay, I continue. Sorry. So the other point, this is an achromatic instrument. What does it mean? We have what we call the Sterney-Turner. I never know how it is pronounced, even in English. This is a Sterney-Turner architecture, which means that we have the light source here, which is given to a mirror, a first mirror, the M1, which collimates the beam. Okay, then we have a parallel beam after the mirror that is sent to the grating. So we can rotate the grating to change the wavelengths we want to observe, and then it is sent back to the secondary mirror. Sent again to a cylindrical lens. This lens has to correct the astigmatism that there is in the spectrum. So if we remove this lens, we have a very wide spectrum. So this allows to have a very thinner spectrum in the image. Okay, and then we have the sensor here. So you can see, you see that the instrument is small, and you can see that the distance between the CCD here and the lens here, and even to the grating, in fact, is very small. So it means that we absolutely need to have cameras with a short back focus. Okay, and well, by the way, run again, the ASI 6200 has a too big back focus, and it is not compliant for this reason with the Uvex. And this is a pity because it's a wonderful instrument. But well, I hope that we'll have, this is probably also the first chip of the new generation, and I hope that we'll have so good sensors with in smaller camera with a shorter back focus. Okay, so this is the idea, and what is very important, it uses only mirrors. Okay, here, and even the grating is a mirror grating, reflective grating. So it means that all these elements has no chromatism. So it means that the focal plane for the image is the same at any wavelength, and this is what makes possible to go so deep in the blue and in the red. Okay, so the drawback of the architecture is that we work out of the axis with cylindrical mirrors, which has some optical defects, and this makes things not so simple. So one of the key of the instrument of the architecture is that we have the same mirror and we have a symmetry between the two mirrors that makes that the secondary mirror compensates part of the optical aberration of the first one. So this is why we have exactly the same focal length for the two mirrors. These are exactly the two same mirrors. Okay. Sorry, maybe I missed something. Yes, something important here. So we have only, this is an achromatic instrument because it uses mirrors. Well, okay, you can tell me there is some glass here with the lens, and this lens has some chromatism. Yes, that's right. But again, this is a cylindrical lens that makes to make the spectrum thinner, and this chromatism effect in this lens is almost negligible. Okay, and of course, what is important is if you want to have a purely achromatic chain, you also have to use an achromatic telescope. Okay, and the best for that is to use a Ritchey Chrétien, which has only 2 mirrors, so there is no glass, there is no window anywhere in the path of focal reducer or only one, and it works. A Ritchey Chrétien works at f8, which is just perfect for this instrument. Okay, well, these are some spots from Zemax for who is familiar with that. The idea is that we can see the achromatism by the fact that at any wavelength, well, even it's not, we don't go to the blue, but I could go down to the far blue, and the spot size is the same, almost the same all along the spectrum. Okay, but something interesting, if I take this value and if I change the aperture, so in this case it is f8, here this is f6.5, and here this is f5, and we see immediately the degradation of the spots. Okay, so it means that if you work at f5, you will have a result, but you will probably decrease quite significantly the resolution. Okay, so again, if you have a f5 telescope and you have no other solution, it will work. But if you want to buy a telescope to use the Uvex spectroscope in best conditions, I really recommend to use an f8 or even f10 telescope. Okay. About the slit, very quickly, so we'll use all the existing slits from ALPI. So we have 10 microns for if you want to have very small instruments. The standard is 23, and we also have 35 or 50 microns if you want to put that on a bigger telescope and catch a very faint object. So at the cost of decreasing the resolution, of course. And we are working. So we have worked with our slit manufacturer, and we will have very soon a new slit with a wider surface. Maybe you know that if we use some guiding cameras with the IMX 174 sensor, the sensor is a little bit bigger than the mirror, the slit itself, which is a pity. So we have increased the size. But most important is that we will replace the chromium by protected aluminium, and then the reflection will be much better. And we will put in anti-reflection air coating that covers the deep blue, and then will improve the performance in the blue part compared to standard ALPI slits. Okay, so I already talked about that, about the telescopes. The best is to use, oh, I look, there is Lee Redmaker, Alain, that I just invited from the waiting room. And the best telescope is really to use a Ritchey Chrétien because it is a purely mirror telescope at f8. The standard slit is a 23 microns, and again, you can, if you want to use the Uvex on a bigger telescope, you can do it, but it's better to have a bigger slit, and then you will decrease the resolution of the instrument. Okay, but again, depending on your scientific program, it may be the good choice to lower the resolution and catch a fainter stars objects. Okay, I didn't talk about that. Well, I told you that the Uvex itself has no guiding or calibration module because we reuse the existing ALPI guiding and calibration modules. Okay, and so the attachment to the telescopes is made through these modules, and mainly you can use it either through a T-mount thread or with a 2-inch nose piece. We have the two solutions, and we can also, I told you, adapt a fiber adapter if you want to work on the bench. The next, regarding the acquisition camera, so we know that we have, well, we really recommend now to use large CMOS sensors because the length, the physical length of the spectrum can go up to 20 millimeters, roughly, well, 20 millimeters. Well, above 20 millimeters, we will have some vignetting. And today we can find CMOS sensor, which are quite affordable with a so long CMOS sensors. Well, we know that it can work with the Attic Horizon 1 or the ZWO ASI 1600 or the QHY 163. We also have all the cameras with the IMX 183. I think this is an IMX, I'm not sure. So you can find it at ZWO or at QHY. And by the way, if you still have an Attic 460, it will work, okay? And for sure, we'll have a lot of new cameras to come in few coming months, years, and so on, because the CMOS will change very fast. Okay, so the main constraints we have is we need to have a short back focus, and so which is a 13 millimeter maximum, which is quite common for most of cameras today, but some of them are, again, the big one from QHY and ZWO have a bigger and too big, in fact, back focus. And again, you have seen this is only for optical reason. This is not negotiable. And we have designed the adapters for these three camera brands, while considering that within a brand, the camera attachment is the same, and then the focal length, the back focus is almost the same. Okay. Of course, we will use we will provide a Demetra version for the Uvex. Demetra is our software, in the Sheliak software for acquisition through the ASCOM drivers and for data reduction. So, you know, this is a software that we made to operate easily our instrument. So we'll have a version for the Uvex. It is under development right now. And the beta version, the first beta version, will be available with the first run of Uvex. Okay. And by the way, this software, Demetra, is with Windows only. I hope that one day we'll have something under Linux, but not for the moment yet. Okay, now let's talk about dates. I'm close to the end of my presentation. I try to look at Alain to make sure he's not too nervous about the timing. So what we'll do now is, so we have the prototype, and we have made some changes based on the prototype, and we are on the way to validate these changes. And so this is really, we are at the end of the process. The next step is that we'll run a first small run of 10 units to make sure that everything is okay, to validate all our documentations for the manufacturing, for the end user, the software, and so on. So what we decided to do is to have a small run of 10 units. And the idea is that we want to find a few pioneers from you that are okay to start this adventure with us. And well, of course, the instruments will be perfect, and will be we look at them with a lot of details, and that will be perfect. But the idea is that if you're interested, please come to us, and we'll do this first one together. It will help you, of course, and it will also give you some advantages. And this is I love this kind of win-win case. The mass production, I cannot say really mass production, but the off-the-shelf instruments will be available in May next year. I hope it will be sooner, but this is very, very realistic. And we work to have the motorization module for sure by the end of next year, but in the second half of 2021.
Francois, will the motor module retrofit?
Yes, sure, of course. Yes, yes,
Okay,
yes.
just
Yes,
wanted
yes,
to be
yes,
sure.
yes, yeah. Yeah. This is a good question. Yes, we'll do it. And in fact, maybe you have seen in this. Well, I will go. Yes, here it is. Well, this is a quick view in the corner. So this is very preliminary, so it will not be the same at the end. But the idea is that we have already put the things, and we have designed the system in such a way that we know that the motors will be compliant with it. So it will be, you'll be able to retrofit and to upgrade your instrument even from the first run. Okay, and so now if you want to be part of the 10, so here are the conditions. The price will be 3,800 euros without taxes and shipment and so on. And so this is the price of the instrument. It will be the same price for the, well, maybe we will adapt it when we'll have the final cost from all the parts, but it will be, this is the price, the same price as the series. And you, on top of that, you may have, if you start from scratch, you may have to add the guiding and calibration modules from Alpi. If you don't have already one camera, you may have to add it also. And if you want to, you can add some grating modules, and they will be available also soon. By the way, the grating module will come with it is the grating plus the holder and plus a small box to protect it during shipment, and you can store in good conditions and so on. Okay, and then so the conditions, but maybe Alain will be more familiar with that, is to pay at the order, and then the shipment is expected in next January. If it can do sooner, it will be. We are rushing. I hope it will be sooner, but it is more reasonable to say in January. And of course, you'll have a priority for the motorization module. And also, I didn't put it on the paper, but I can tell you that you will have this magic new slit with the better reflections and air coating and so on. Okay, which will be included. And I think that this slit, because it will be more expensive than the standard one from LP, I think this will be an option in the future. Yes.
Question. I may have missed it. Did you, is there going to be any grading included with it, like you
very good point. Sorry, no, I didn't tell you. The standard module, will be the 600 groove per millimeter. Okay, so this is and it is shipped with the grating, of course. Okay, and the standard, all the Uvex will be shipped with the 600. If you really prefer to exchange it with another one, you can ask us. But this standard will be the 600. Okay, which gives a very medium range resolution. I think this is the good choice, and probably where the Uvex quality is the best. Okay, so this is for the when the problem will be the product will be available on the shelf. Well, regarding the future developments, of course, we'll work on the motorization. We had already started to work on it, but we still have things to do with it. What I can tell you is that it will be it will use some stepper motors, and we are working currently on the electronics to control things. And the idea also is to have something which is controllable through ASCOM. It will be controlled by Demetra, of course, but it will be also controllable through ASCOM driver and Indy driver under Linux. Okay, and we are also thinking about proposing other gratings with the same density, but with the different blaze angles, because if you want, most of all the gratings that will ship will provide in normal conditions will be blazed at 500 nanometers. And but if you want to observe in deep blue or deep red, maybe it's better to have a UV blazed grating or higher blazed grating, and we'll do some tests and we'll propose very probably other references. And also, so we will test the new slits, but so the new slits will be 23 microns, and if the results are where they're expected, and if you need well, all the users need other widths, then maybe we'll do them in the near future. That's it. If you have any question, it will be a pleasure.
Quick question, François.
Yes.
Since this comes up a lot in discussions, that what material you're using, metal, and some people are wanting to see more composite in certain regions because of the temperature, the effects of temperature on your you know, positions and your frequency positions. Any comments or about that?
The material is aluminium. So we have most of parts are in aluminium. The main parts that I showed you is in aluminium, and the sheet metal parts that makes the base and the cover are in aluminium also. And well, the first feedback we have from the prototype is that it is not very temperature sensitive. But what I know, and I think that the reason is very simple. This is because the instrument is small. So, and if it is small, then it is less sensitive to the temperature. And on top of that, the fact that we can refocus the instrument, I think this is a very good security. So I think that with that, it will work. Okay, now I don't have enough experience to tell you exactly how many times I have to refocus during the night.
One last question, then I'll give the floor to someone else. In your resolution slide, you made all of your theoretical resolutions based on 5.6, but you suggest 5.8 being the optimum focal ratio. Do you think it would be better for you as you present this product to use the F8 numbers rather than 5.6, so you don't get a bunch of questions?
Yeah, in fact, what we did is that during when we did optimize the instrument on the optical system, so in Zemax system. So when we did the optics, we did the optimization at f6.5. Just to be somewhere in the middle between f5 and f8. Okay. All what we know is that if you go at f8, it will be better. Okay. Now, how much better? I cannot tell you exactly. I'm quite confident that the figures I've shown are quite conservative, and the results will be at least these values. Okay. Now, well, we need to do more experiments, and in coming weeks, we'll make our own measures with different gratings in different conditions and so on, and I will have more values.
Overall, okay. That was a wonderful presentation, and I think it's going to be a great sales tool for you.
Thank you.
I will step out now and let someone.
Thank you, Ron.
So, okay, I have two questions.
Okay.
Or are we both talking here?
Yeah.
The first one is there a focus mechanism for M1?
The answer is no. No, we just count on the mechanic. Well, you know, no, we consider that the mechanic will be close enough to be in good condition. What we have seen on the prototypes tell us that it works fine. So we don't need to have any focusing on the M1. Okay,
and then the other question is, the order sorting filter is a mechanical insertion. You're not going to make that robotic?
No.
Okay.
No, it's a good question, but again, there is no room. It's very dense, it's very small, and there is no. I know it could be useful. That's right, but no. In fact, we have put a standard thread from Tor Labs. Maybe you know that it is a SM05 thread, which is a half-inch thread, and then you can put a half-inch filter on it, which is standard, which exists in standard. And that we will provide very probably, of course.
Oh, I guess one more question on that. Is the order sorting filter included with the Uvex, or is that an option that we have to purchase?
It's a very good point. I didn't think about that. I think it is not in standard, but that's a good point. And well, yeah, I can see that. For the first one, it will be included.
On your website for Uvex, you said that you installed the CMOS detector. Is it linear?
Yes. I think yes. I think yes. You know, the question of the I've seen some. Generally speaking, the question of the CCD versus CMOS camera is a very wide question. For sure, we are switching from CCD to CMOS. We are somewhere in the middle today, so it's quite difficult. But I like to say that from a performance standpoint, maybe the CCD is still the best one, but it's less and less true, especially with this new generation of CMOS camera that arrive. And for sure, if you look at the price performance ratio, then the CMOS is far in front of the CCD from now. So it really depends what we are looking at. Generally speaking, a CMOS is very linear. I've seen some people recently saying that there are some gaps in the steps in the linearity, and it looks to be, I think, a software problem inside the cameras, as far as I know. But I don't have a lot of, I don't have more information than that. Okay, what I know is that for sure all the cameras will switch from the CCD to CMOS, and there is one thing which is quite sensitive, which is what we call the telegraphic noise in the CMOS camera. So you know, you can have light hot pixels, but hot pixels that are moving from one image to the next one, and then you cannot correct this problem the same way as with the hot pixels on CCD. So we have to adapt the software to make sure that, because of course the Murphy takes care of that, and it will put the bad pixels on where there is an important signal. So it's not obvious to switch directly, but we're working on that way in Dimitri. Yes, one.
Actually, I was hoping Arnie would give us a little hint of some of the research he's been doing, because he certainly sold us on moving to the CMOS for our photometric work. And as you know, Anatole, it's pretty important to be linear. And he sold me. So Arnie, would you share a little of that wonderful research you've been doing this past year?
Oh boy, I mean, that's another talk entirely. But
Yes.
But yeah, I agree with Francois that CMOS is not just the wave of the future, but over the next year or so, I think it's perfectly reasonable to purchase one of those cameras.
Yeah, I've done extensive testing with the QHY 600s, which are essentially the Sony chip, and as long as you have a 16-bit A to D, they seem to be very reproducible. If there's a little bit of nonlinearity, you can calibrate it out. So.
Yeah, you know that, well, Christian Brill, who is again involved in our instrument, he's working a lot on the cameras and currently testing a lot of cameras. For him, for sure, the CMOS it is from now, it is a solution. And maybe you can see on, I can give you the link to his last webpage regarding the ASI 294. I think, and the one with which he made the spectra I showed you at the beginning of my presentation. And it makes a lot of different measures. And again, the CCD time was stable because the CCD technology is now stable. In the CMOS, we are still in a very active period, so very probably each month we'll have new sensors and we'll have to change to be very careful. What is sure is that it will be better and better and cheaper, so we can run fast and that direction.
Thank you.
Any other question?
I have to say, for the features that you're providing, it seems like a very reasonable option out there, because there's really nothing else out there that is not either, prototypical, one of a kind, has uniquely made for each scope. Once again, I think you've hit on something that's going to work. I think using it on the plethora of F8 rich accretions that are going out, I think that's going to be, it'll be a good product for the small telescope people. We're going to be using it to do support for our project at Mauna Kea, where we're doing the new quasar catalog. And that quasar catalog includes redshifts that are far longer, far further in the red than we're used to. And this spectrograph might even be able to allow us to look at some of these lines that have shifted so far. They're beyond what we normally can see in a normal spectra. So I'm excited about the possibility of this spectrograph. And Arnie's comment about the filter, I think that becomes important, because you're going to start seeing the mixing. You'll see the mixing there. Yep. in those, and so if we can do that, that'll be a great presenter for our undergraduate and graduate students to kind of give them an idea of what we're actually having to deal with these far redshifted quasars.
What wavelengths you are looking for? Oh, sorry.
I'd just like to add that I think that your choice of the Czerny-Turner design is great, because it lets you to optimize the alignment both ways rather than trading them off.
Sorry. The line is not very good. I didn't understand all what you said, Bruce.
Oh, I said the Czerny-Turner design is a good choice, because you can align both the ingoing and outgoing mirrors to align with the grating much better than having to settle for something in the middle.
Yeah, okay, I understand. That's right, for sure. But well, I told you I'm a mechanical engineer. I am not an optical engineer. So I know I'm able to do some calculation with the Zemax and so on. So I know quite have good basement for good background in optics, but I know I will never be an optical engineer. Anyway, what I know is that there is no ideal, there is no perfect optical solution. So all architecture has advantages and drawbacks, and the Czerny-Turner have a lot of good advantages, but the litho architecture also have well. Again, we all find the best one, but well, we used to say that we can define the best architecture for a given setup, for a given scientific goal, scientific program. But I think this option for me is a very multi-purpose instrument. You can do a lot of things. If you want to have a very optimized instrument for one given kind of observation, maybe it will not be the best one, but it will allow you to do a lot of things.
Oui, d'accord.
Oh, let's continue in English, because if you switch to French, nobody talks anymore. Well, and if there is no more questions, I'm interested to hear each of you, or if you want to say something about, do you think that which kind of observation you would be able to do with it? So does it really opens new doors for you? I know well, it's maybe it's an impressive question, but I'm curious.
Well, definitely observations of the Boulder jump are very interesting and important.
Okay.
So that's for sure.
So in far blue, then in far blue.
Yeah. Mm-hmm.
Okay.
I would say that, like, logistically being able to control it remotely will be a big advantage. So I set up a remote observatory just this past year. We have a robotic telescope about an hour out of town, and so the possibility of setting up a spectrograph that's controllable out there is that sounds great. I'm wondering, actually, one of the questions that I had was about finding the slit. So, like, is there, with the L-Hires, for instance, there isn't an LED on the slit to be able to find the slit when we're in the guider image. And so how would we, if I'm controlling the telescope remotely and I want to get the star right on the slit, how will that work?
In fact, this is outside of the Uvex. Again, the Uvex will use the LP guiding module and calibration module. And if you use both, in fact, there is no LED in the LIRIS. There is just the calibration lamp. And with the LP guiding and calibration module, you can do the same. You just switch on the calibration lamp, and then it will illuminate the slit, and you see it perfectly in the guiding image.
But it's not too bright, you can still see stars? Or do you have to turn it on and then you can see where the slit is, and then you need to know where your pixels are?
Exactly. So exactly what I'm doing at home. Well, by the way, I am installing my telescope and I want to use it remotely. So all the remote features will be available soon because I need them. No, you just have to switch on the calibration lamp. Then you see immediately the slit. You can measure the exact position of the slit in the image, and then you put, well, I'm using PhD2 guiding for the guiding system, and I put the slit exactly where I want, and then I switch off the calibration light, and I let PhD doing the guiding.
Right. Yeah. Oh yeah. I was wondering, with the image that you showed of the setup there, you had a guide scope and as well as the guide camera on the Uvex. You're not using both of those at the same time, are you?
Well, it really no. In fact, well, this is not my setup. This is the setup from Olivier Garde. But you know, when I start installing my own telescope, which is a small telescope, it was a C8, and I just switched to a Ritchie Chrétien RC8 inch. To have an RC telescope for the test, and at the beginning I thought that I would need a pointing camera, so a wide angle camera to see where I am in the sky. But it appears that I have a mount. I have 10 micron mount, which is just perfect, and the precision is good enough. And when I point to a star, it is always in the field. And in fact, I don't really need the pointing camera. But my plan, I don't do it yet, but my plan is I prefer to have this pointing camera, because in any case, when I do an observation, an automatic observation, I will take an image of the field of view to be sure that I'm looking at the right star. Okay, but this is a control. This is not to find the star.
Yeah.
Now, if you have a bad mount, in the past I had a bad mount. I didn't need to have this pointing camera to see where I am.
Yes, right. I wasn't. I hadn't thought of that. So the guide scope or finder scope there is really a finder scope. It's being used for bad pointing. Okay.
Yeah. Again, it depends on your the focal length of your telescope, and of course.
Yeah.
Okay. Thank you.
Thanks.
Any other comment?
I had one more question. That is the acquisition guide field of view. I know you can't specify it in arc seconds or arc minutes, but can you specify it in millimeters of area or something so that we can do our own calculation depending on our focal length?
Yeah, the current LP slit has I think the dimension is 10 by 10 millimeters. The mirror itself. Okay, and in the new design, and with 10 by 10 millimeter, with a new CMOS cameras that we recommend, like the QHY 174, the chip is a little bit bigger, and then the new slit will be 12.5 millimeter wide instead of 10, and then it covers all this chip. And by the way, this is the right chip for guiding today. I don't know what it will be in 1 year, but okay.
Is there any camera in the offing that has better UV sensitivity coming up? I mean, well, I don't think that's their primary business.
No, but we have to recommend a camera, and today our decision is not made yet. We know it will be most probably one of the camera that I did mention, either from ATIC, ZWO, or QHY. I don't know which one yet. What I've understood is that well, we know that the biggest sensor, the better, because the spectroscope itself can work even with a wide sensor. So the decision is not made yet, and of course there is a question of price, and depending to who you are talking to, the price is important or not. So. Do you know already which would be your choice, Wayne? Do you know the camera enough, or?
No, there was I have a couple Finger Lakes cameras that have, I don't remember the exact chip number, but it has considerably better UV than most other chips. But I think they're roughly 6 micron type pixels. But okay. I don't think it's going to be available anymore, so it becomes academic.
And again, be careful with the back focus. So we have
no,
a strong
I
mechanical question.
Yeah, Finger Lakes and all those other people have really deep back focus, so that wouldn't work. You'd have to
so forget it.
Remount the whole thing, which is very hard to do.
So it's less than 14.4 then, right? I believe that's what that the back focus is on the ASIs, right? 14.4.
Well, all the camera I did mention are compliant with the Uvex. We know that. In some of them, you have to remove the front adapter. So it's not easy to understand exactly what is the back focus and how it works and so on. But what I've realized is that the camera will work. But anyway, all the cameras I mentioned, we know that they are compliant. They are compliant. And I know that some of the new ones, like the ASI, I've seen. Well, Christian Brill did ask me for an ASI 268, I think, which is a new one, which is only available in color right now, but it will be available in black and white probably. And it is the back focus is too long. It seems to be too long. It's a pity. It's a pity.
I'm looking at the 294 specs right now, and it says that the back focus distance is 6.5 millimeters / 17.5. So that's probably where you have to take that. adapter.
Yes, you have to remove the front adapter.
Yeah,
that's quite a clever system, in fact, because they did a good job.
Yeah, and then they only show the quantum efficiency graph down to 400 nanometers, but it is at 65% there at 400. So
yeah. Well, you know, well, as I've written in one of the slides, I think that we are just limited by the cameras, and when we are playing with the limits, and at these wavelengths, everything becomes quite unknown. Like all the, for instance, in front of the camera, you have a window. On the window, there is very probably an air cutting. In some case, the air coating is cutting before in the blue part, and then you have to take care of all these small details, and this is very complex. I can tell you that, in fact, I told you that this is a fully achromatic instrument. In fact, there is one piece of glass that the light has to go through, which is the slit. And the slit, we did work on the slit because we have seen that in the deep blue, if we don't change the slit, we have a quite significant loss. Just it's a pity for few tenths of millimeters, and so you have to. A lot of things are new, in fact, and you really have to push the walls everywhere. Any other people wants to talk? No, that's it.
Looking forward to trying it out.
Great.
Okay, thank you for all of us for to attend this meeting. Of course, you will receive a copy of the presentation, and I will send you a link for the recording of a meeting. We try to record, and normally it's fine. So you will have a link to have it.